Good afternoon, everybody. We represent IITM Pravatak, Technologies Foundation. We come from IIT Madras. And the topic we've chosen for today is somewhat of an experimentation exercise that went on for quite some time in IITM with a few of our team members. And so we thought, how can we make things more efficient with regard to overhead, bandwidth, and latency? And we finally came to a conclusion that we need to have an experimental approach to replication performance optimization in Postgres. So what is this exercise? What does this experiment entail? This experiment entails incorporating multicast in replication in PostgreSQL. What we've got so far is TCP unicast, which is very inefficient in terms of overhead, bandwidth, as well as latency. And we wanted to bring in the beauty of multicast and marry it with the DBMS internals. So we get a sibling from that marriage that is more optimal in terms of overhead, latency, and bandwidth as such. So we in Postgres are stuck with TCP for quite a long time, right? And this leads to a number of low limits on the number of replicas that can be supported. If you look at the literature, they'll say some of them have 15 replicas in a single Postgres DB instance. That's the maximum limit up to which you can go to. And then you've got other variants that talk about having just about 5 replicas as the maximum. This is because of the fact that if you want to create 15 replicas from the primary, you have to have 15 different TCP connections going to each of these replicas. So that is very inefficient, right? Because it's inefficient because the amount of bandwidth taken in terms of kernel buffers being used on the primary, the amount of bandwidth taken up by these 15 connections is overwhelming. And the primary also has to have a bandwidth effect on the NIC card, the network interface card that's sitting on the primary. And depending upon whether the replicas are all sitting behind one single router or a couple of routers, the streams will be replicated on each of the paths to the various replicas. And that is going to create a large amount of bandwidth saturation as far any point in the network is concerned. We just search for the upper limits as far as read replicas are concerned. Some of them say 15 read replicas within the same region can be had. But then again, if you're doing primary to multiple replicas, the load on the primary is going to go really high with 15 read replicas. So if you want to send something on a TCP connection, what do? You copy the contents of the user mode buffer to the kernel mode buffers, and from the kernel mode buffers, the TCP stack, which is part of the kernel, takes that information and sends it to the replica. And if you've got 15 replicas sitting behind a single router, right? Then all the 15 connections will follow the same path on the network and hit the replicas behind the single router. So that this means that you've got bandwidth saturation all along the way from the host, which is the primary, to all the way to the replicas, right? And so bandwidth is a problem as far as every link is concerned. in the replicas, in the path towards the replicas, right? So now we introduce what is the primary difference between unicast and multicast. Multicast, just think of it this way. You have senders and receivers. And in the variant of multicast we're going to use PIM bidirectional. PIM bidirectional means any sender can be a receiver and any receiver can be a sender. We want to use that powerful tool like PIM bider in order to make this happen. So that protocol essentially gives you the flexibility of every receiver being a sender and sender being a receiver. So let's look at unicast first. In the top diagram, you've got one primary with 3 replicas on the right hand side and the topology of routers in between. If the primary has to send the replication mechanism, as whether it's doing synchronous replication or asynchronous replication or any other type of replication, it has to send all the 3 streams from itself all the way to the next hop router A, right? And from there, depending on whether these replicas are sitting behind one single router or distributed across multiple routers, you will have situation like this where from A to C you have two streams, and A to B you have one stream, and so on and so forth till the split happens at C, D and E and goes to the replicas. So now you can see the bandwidth saturation between the link A and C and between the link between the host, which is the sender, which is the primary, and router A. But if you look at multicast, the beauty is you don't have to send 15 different replicas, 15 different replicas the data based on 15 different TCP connections that you're opening. You just open a single multicast socket and you just pop the message inside, right? And as if by magic, because of the replication going on inside the routers, it just beautifully replicates to all the receivers. And notice that in the links between A and C, A and B, C and D and C and E, there's only one copy of the entire stream going. But what is the downside to using multicast? Reliability. TCP is a mechanism by which reliable transport can be made possible. But if you've got multicast, it's usually used based on UDP, right? But things are changing in the standards bodies. You've got situations where people have come up with a protocol like QUIC, for example, which is a UDP-based mechanism, but with the reliability features of TCP built in. And there are even some drafts which are currently going on in the IITF that are talking about running QUIC over multicast. If it's QUIC over multicast, then if I've got multicast reliability built in, the TCP reliability built in inside multicast, and I've got standards bodies which are working out other proposals in order to make reliability a good, strong aspect of multicast, right? So this is how the distinction between unicast and multicast is. So we're going to use protocol independent multicast bidirectional. Bidirectional meaning every sender can be a receiver, every receiver can be a sender, right? So if you've got a primary and a secondary, multiple secondaries, they can work in such a way that they are representing the situation where you've got a single primary and multiple replicas. It can also work for the condition called multi-master replication, where every sender can be a receiver and every receiver can be a sender. And in multi-master replication, you come across the problem called full mesh, where all the nodes which are part of the multi-master configuration, they will exchange writes between each other in a full mesh fashion. Suppose there are 3 nodes, then a full mesh is n into n minus 1 by 2. You will have three different connections going if you're using TCP unicast from every node to every other secondary node. or every other multi-master node. But if you do it using multicast, using a beautiful concept called senders, receivers, shared tree, and then replication by routers, these 4 concepts will build a very efficient multi-master configuration, right? So this is not new. PIM BIDER is being used in the industry for distributed collaboration, financial applications, real-time group communication, and so on and so forth. So if we efficiently stream changes from a primary to multiple using multiple standbys using multicast, you will reduce the TCP overhead on the primary, you will reduce the TCP overhead on the NIC on the primary, you will reduce the bandwidth requirements from the network, because only 1 copy is being sent, wherein 15 copies were needed for 15 replicas, and you will reduce the latency as well, right? So assume that it's the number stupid, right? Assume that 1 gig of data being sent from a master to multiple replicas, or in the multi-master situation, they want to exchange the traffic, right? So either it be multi-master or it's primary standby configuration. Assume that 1 gig of data is being sent to 15 different replicas by the primary. This is what will happen. On the right hand side, you see TCP case, the kernel buffers will take 15 gig worth of buffer space. Network bandwidth at the NIC will be another 15 gig on the primary. Network bandwidth at any given link in the topology of routers will be 15 gig worst case. Assume that there is 1 master and multiple standbys all behind a single router, right? So to reach that particular single router, which is the first hop router from the replicas, all the streams will have to cross the same set of links. So in the 15 gig is the worst case there, right? And CPU time quantified, again, it's a multiple of 15, right? So now you look at how the multicast case is built up. The multicast case is built up 1 gig of data, that's about it. You open a single multicast socket, you send the traffic through that socket, and automatically the routers in the intervening topology will replicate the traffic and send it to the replicas automatically. Network bandwidth at the NIC card on the primary, which is sending it, it will be again 1 gig. Network bandwidth, it will be 1 gig worst case, nothing else. And the CPU time again is 1x. So obviously there are benefits in going with this. But what do we require for making this happen? Right now this is in an experimental stage. We are probing the possibilities of how to get all the concepts of reliability that TCP represents into multicast, right? And we're trying to incorporate mechanisms from various standards to build out a situation where the overall throughput, the bandwidth, latency, and everything else that needs to be optimized is possibly optimized using multicast. You have to create a multicast module to push the changes. You need a multicast sender. You need a multicast receiver. And in this case, since we're choosing PIM BIDER, every multicast sender and every multicast receiver can be the same. They can be, any node can be a sender as well as a receiver. And of course, we need an efficient error recovery mechanisms that need to be implemented. Consistency, some form of negative acknowledgement. You have time? Okay. So some form of negative acknowledgement mechanism should be built in. And checksum validation, of course, at the network layer level, at the data link level, is already available. And we have to implement the concept of something called a designated local repairer as in pragmatic general multicast. Suppose you're sending packets to 15 replicas, and the packets of one of the packets get dropped somewhere on the router, and you have to recover from it. The way you do it is you designate a node called a designated local repairer in certain localities in the multicast shared tree. And that the function of the designated local repairer is nothing but to keep all the packets that have been received over a period of time or in a certain time window within itself. And when the receiver detects that it has lost one packet or two packets or three packets, it will basically send a negative acknowledgement to the designated local repairer. The designated local repairer will look in its packet cache and then take that packet and send it back to the node that requested with the NAC. Right? So these are all mechanisms which have already been detailed out in several RFCs. RFC 3208, for example, talks about pragmatic general multicast. So we are picking up the concept from there for the designated local repairer. You've got sequence numbers and other helper items that can be incorporated into the multicast stream even though it's running on UDP to make it as reliable as TCP. And as far as conflict resolution is concerned, you can pull the missing wall entries from the designated local repairer as already specified. Failover management. There, it's really exciting because you've got a single multicast group. All the senders and receivers are partaking in the multicast group. Every sender can be a receiver, every receiver can be a sender. The primary goes down. What do? If the primary goes down, the secondary takes over. Now, do you have to change the multicast group? No. Every sender is a receiver, every receiver is a sender. Right? So you pick up where you left off. Automatically, the new primary will start transmitting the changes, its wall changes to everybody else. So it's seamless transition. And of course, you will have missing wall entries happening, an error recovery mechanism that will kick in to get the stuff from designated local repairers and other entities. Suppose the designated local repairer does not have the capacity to hold that data for some reason, right? The NAC will automatically be sent to the primary, and the primary can look in its data cache and send the packet over to the requesting replica. So advantages. Instead of one-to-one TCP connections, the replication is done through multicast with appropriate latency and bandwidth optimizations. Postgres buffer utilization on the primary, especially the kernel buffers, I showed you in the 15 gig example, right? They are optimized. Higher number of replicas can be supported. And you can have multiple multicast groups with each having its own subscribers and publisher configurations working on multicast rather than on unicast. That's another beauty that we can think of. Then seamless transfer of primary to secondary without changes to multicast group. Addition of designated local repairer is used to save packets. Primary is the fallback for the DLR. So what are the challenges? We have to test this thing properly. We have to make sure that whatever modules that we're building into Postgres are error-proof and recovery mechanisms are in place for this to happen. Network complexity. Setting up PIM-BIDER multicast routing requires network switches and routers that have to be configured with multicast. And of course, data integrity is important. Then using multicast could be more challenging than traditional streaming replication. So this is, conclusion, this is an innovative approach that could offer high bandwidth efficiency, but we require a replication mechanism to be built into Postgres. Network setup needs to be done. Administration tools in order to maintain data consistency, error handling may have to be developed. So this is the PIM-BIDER specification, RFC 5015. If anybody is interested, you can take a look at this. And RFC 3208 is the pragmatic general multicast, which introduces the concept of designated local repairer. That's all I have. Any questions? Any questions? Yeah. Can somebody give me a mic? Sorry, I'm not able to hear you.
Thank you. So is this kind of the same concept that we kind of see in NoSQL databases like Cassandra, wherein you have a clustered type of a setup, wherein no node is particularly dedicated as a master node?
You can use this for multi-master replication as well as master replica information situation.
Okay.
You can use it for both.
Okay. So
Just think of it as a magic pipe between all these entities where only one copy goes in from the sender, everybody else gets it. So it can be master replica kind of a situation where you've got a single master and multiple replicas, in which case the master is the controller of the multicast group and he will send the changes to all the replicas. Or in a multi-master replication situation where you've got 6 or 7 nodes having full mesh connection with each other, each sending the changes to every other node.
So this can also be used for a multi-sharding kind of a problem?
Absolutely, absolutely. Multi-sharding can be used. You can use it. You can have master and replicas for sharding itself. So sharding is a concept where you will split the table and put it all over the place, right? Right? So herein you can have master sharder and a secondary replica sharder, multiple secondary replica sharder, put them all into a multicast group, and lo and behold, you've got the whole thing going.
Thank you.
No problem.
If there are any more questions, we can take them offline. We're going to take a quick 1-hour break for lunch, and that's downstairs at the down layer. It's Ceres, so yeah, please enjoy the lunch and be back. Thank you.